Good afternoon, everyone. I'm Jiaxin Chen from State Key Laboratory of Transducer Technology, Aerospace Information Research Institute, Chinese Academy of Science. Today, I'm going to talk about a high-performance mode-localized vacuum gauge based on FPGA closed-loop control. First, let's go to some background on vacuum gauge. The vacuum gauges are used to measure the gas pressure below atmosphere and can be divided to many gauges according to the gauge pressure range. Here, we aim at a median vacuum gauge, which measures the pressure below 1,000 Pascal. These gauges have been widely used in semiconductor equipment and even spacecraft. There are two types of gauges that can measure the median vacuum gauge pressure. They are capacitance diaphragm, especially ceramic diaphragm, and resonator-based gauges. The ceramic diaphragm capacitance gauge is a gold standard in median vacuum pressure measurement. It measures the pressure based on the capacitance changed by diaphragm deformation. Inficon and MKS are the two famous manufacturers. Their products have the advantage of high accuracy and stability. However, the fabrication process is complex and secretive. Besides, a heater is needed to achieve the performance, so the power is high. Resonator-based gauge has been studied for many years. It contains several types. Among these gauges, traditional resonator pressure gauges are famous, and the mode-localized gauge is a new hotspot. Now, let's look at how resonance, weak coupling, and mode localization work. In short, mode localization is a special phenomenon of multi-DOF coupling resonators, while the coupling strength is weak enough. Specially speaking, the figure shows a spring mass damper model of a 2 DOF. We have two resonators and couple them with the coupling spring Kc. If the size of the two resonators is different or the coupling string is 0, the two resonators will vibrate independently. According to the formula, both of them can measure the stress individually. This is the principle of traditional resonator sensor. Once the two resonators are identical and the coupling string is weak enough but not 0, this resonator is called a weak coupling resonator, WCR. The two resonators work as a coupling system and have two basic operation modes, which is shown as two peaks at the figure of frequency versus energy. At the time, the energy is equally distributed between the two modes. Then, if we apply stiffness perturbation, delta K, on coupling system, the energy will localize to a certain resonator. This is called the phenomenon of mode localization. It's used in MEMS sensors by Splitter for the first time. Unlike traditional resonator sensors that only output frequency signals, WCR has amplitude series output, which stands for the energy of the resonator mentioned before. According to the governing equation, the various output metrics are obtained. The frequency changes a little with the stiffness. In other words, the sensitivity is low. Similarly, the characteristic of amplitude series output can be obtained. Studies show that the amplitude radio output, AR for short, has the advantage of in linearity, sensitivity, and signal-to-noise radio. These can be seen from the right side figures. It's noted that linearity is good only when AR is a little larger than 1 in theory. In fact, if the amplitude of R2 is too small, the AR will be nonlinear where it's too large. What's more, in this coupling system, the total perturbation equals delta K1, subtract delta K2. So when perturbing two resonators, the total stiffness variation equals 0 at present. So the system can reject common inference theoretically. In traditional resonate pressure sensor, the pressure load can cause the stress on the diaphragm, and the frequency of the resonator is changed by the stress. Studies show that this gauge has the advantage of high accuracy in a wide temperature range. However, the fatal flaw is that the relative sensitivity is low, so the lower limit of the gauge is difficult to reduce further. As mentioned before, mode-localization gauge is a new hotspot. Here is a mode-localized gauge. It's famous for its high sensitivity, common rejection, and wide temperature range. However, because of the structure of the resonator, the accuracy and the linear range still needs to be further improved. The table lists the comparison of the above famous median vacuum gauge. It can be found that mode-localized gauge has the advantage of high sensitivity and simple fabrication process and high linearity. The most important is that the accuracy, sensitivity, pressure range, temperature, as well as the resolution can be improved further with the methods in this work or our upcoming papers. Next, the shortcomings of previous arts need to be clarified. First, in previous works, they detect the physical parameters only using one of the multi-DOF resonators. In other words, only single end stress is measured. So it's susceptible to common stress, such as thermal stress. This can be offset by detecting the stress differentially. Meanwhile, the method can double the sensitivity of the differential mode stress in theory. Secondly, parallel plate capacity usually is used for driving and sensing the resonator. The damping in this way is large, so the quality factor usually is smaller than 15,000, which can limit the sensitivity. Besides, the signal is influenced by feed-through, and the signal-to-noise is low, which can also degrade the sensitivity and the linear range. Therefore, the comb finger and the piezoresistive can be used for driving and sensing, which can increase the quality factor. And the piezoresistive pickup is modulable and famous for its high signal-to-noise. So, the above two questions can be solved by the method. The goal of this research is to increase the relative sensitivity, expand the linear range of output metric of the mode-localized sensor, and improve the accuracy of the gauge. The proposed weak coupling resonator is shown in the figure. It consists of two identical main resonators and a coupling structure. Here, the main resonator is an H-type double-ended tuning fork resonator. It has two basic modes, and out-of-phase mode is chosen to minimize the damping. Second, the coupling structure is a slender beam, which makes it possible to adjust the coupling strength without changing the position of the resonator on the diaphragm. The two air-typed piezoresistive strain gauges are used as a pickup structure. The piezoresistive signal can be modulated by the driving current. So the signal to noise can also be modulated. As shown in the figure, the gauge is based on diaphragm deformation the resonator is entered on the diaphragm, while the pressure is applied on the diaphragm. The diaphragm can generate both positive and negative stress. So if we put two resonators on these zones, they can measure pressure differentially and reject the common thermal stress in one. Besides, the resonator is sealed by vacuum wafer bonding, so it's independent of the type of gas. The gauge is fabricated by a standard bulk silicon SOI process, and then vacuum packaged by eutectic bonding. All of these are finished in our lab. The chip after dicing is shown on the left. The volume is smaller than the famous commercial products. Then the chip is bonded on the print circuit and sealed in stainless chamber. The gauge is tested by the developed calibration setup. The setup controls the vacuum pressure by tuning the two precision flow valves, V1 and V2. Then the outputs of the developed gauge are compared with the reference gauge, and the error is obtained. A novel closed-loop control method of the resonator has been achieved. The schematic closed-loop control is shown in the figure. Because driving resonator 1 and resonator 2 simultaneously can reduce the sensitivity, so only resonator 1 is driven. As shown in open-loop response chart and the table, if the pickup signal is detected from resonator 1, the phase parameter of PLL at mode 1 and mode 2 is similar, which can lead the controller not to distinguish between the two modes. However, if resonator 2 is chosen, the phase of the two modes is quite different, so the controller can work at both modes. With the help of this controller, 3 devices are tested. The relative sensitivity ups to 260,000 parts per million. The sensitivity is about 1,000 times of traditional resonator pressure sensors and about 3 times that of previous mode-localized sensors. The sensitivity of the 3 devices is a little different because of the fabrication error, especially the dimension of the H-type double-ended tuning fork and the coupling structure. The hysteresis error is much smaller than that in open-loop configuration. The typical error is 1.70% of the reading, while the vacuum is lower than 10 pascals. While the vacuum is higher than 10 pascals, the error is down to 0.68% of the reading. The resolution of the 3 devices is about 20 micropascals. The value is only 6.7% of that in open-loop configuration. The calculated resolution that make use of sensitivity and the repeatable error is 14 micropascals. The difference between the calculated value and the measurement result is mainly because temperature fluctuations, noise of the instruments, and stability of the set points value. Finally, the performance of the proposed gauge is compared with others as shown in the table. The proposed gauge has the advantage of high accuracy, high sensitivity, and independence of gas types. However, the stability, both short-time and long-time stability, as well as temperature range, still needs to be improved in the future. Thank you.